Welcome to The Explainer. Today, we're diving into one of the coolest shortcuts in all of math, de Moivre's theorem. This thing is a total game changer. It takes complex number problems that look super messy and tedious and makes them, well, surprisingly simple.
All right, let's just jump in with a challenge. Look at this thing, 1 plus I to the 8th power. Seriously, if you had to do this by hand, no calculator, where would you even start? I mean, the first way that comes to mind, yeah, it's going to be a bit painful.
I mean, sure, you could multiply it out, 1 plus I times 1 plus I, get that answer, then multiply that by 1 plus I again and again and again. Ugh, it's so tedious, so messy, and you just know you're going to make a tiny mistake somewhere along the way. There has to be a better way, right?
And thankfully, there is. A mathematician named Abraham de Moivre came up with this absolutely brilliant shortcut for this exact kind of problem. And the whole secret, the key, is to stop thinking about complex numbers as x plus iy and start thinking about them with a distance and an angle, in polar form.
Okay, here it is, de Moivre's theorem. Now, I know it looks a little scary with all the symbols, but trust me, the idea behind it is incredibly simple. If you want to raise a complex number to a power, you just do two things. First, you take its radius, r, and raise that to the power. Then you take its angle, theta, and you multiply it by the power. That is literally it. Power up the radius, multiply the angle. So simple.
All right, now for the fun part. Let's see how this theorem just completely demolishes that monster problem we started with. Let's put this thing to work.
It's just a clean three-step process. Check it out. First, we have to convert our number, 1 plus I, into polar form. When you do that, you find it has a radius of the square root of 2 and an angle of pi over 4. Okay, step 2, apply the theorem. We take that radius, the square root of 2, and raise it to the 8th power. Then we take the angle, pi over 4, and multiply it by 8. That gets us 16 cis 2 pi. And remember, cis is just a handy shorthand for cosine plus I times sine. So for our last step, we just convert it back. The cosine of 2 pi is just 1, and the sine of 2 pi is 0, which leaves us with a super clean final answer.
And just like that, 16. That's it. That huge, awful multiplication problem we started with just collapses into the number 16. Something that seemed almost impossible to do by hand is now incredibly simple, all thanks to this theorem.
But wait, there's more. The theorem's power doesn't just stop with powers. I mean, raising something to a power is just repeated multiplication, right? So what about going backwards? What if we want to find the roots of a complex number? The opposite operation.
Well, it turns out de Moivre's theorem has a sibling, a formula just for finding roots. And it starts out pretty similar. To find the nth roots, you take the nth root of the radius, r. Makes sense. But for the angle, this is where it gets really clever. Think about it. You can go a full circle, that's 2 pi radians, around the origin and land right back where you started. To account for all those possible rotations, we have to add multiples of 2 pi before we divide by n. And by letting this little counter, k, run from 0 up to n minus 1, we can find every single root.
And this is the really beautiful part. The roots aren't just some random numbers sprinkled onto the complex plane. Nope. Every number has exactly n distinct nth roots. So you'll always find 3 cube roots, or 5 fifth roots, or 7 seventh roots. And when you actually plot them, they form this perfect symmetrical pattern. They're all equally spaced around a circle. It's incredible.
Okay, I know that can sound a little abstract, so let's make it super concrete. We're going to walk through a couple of examples and see exactly how this formula uncovers those hidden roots.
Let's start with something easy, the cube roots of 8. Now, obviously, we all know one of them is 2, right? 2 times 2 times 2 is 8. But math tells us there have to be 3 of them. So where are the other 2? Well, when we use the formula and cycle k from 0 to 1 to 2, we find them. We get the obvious one, 2, but then we also get these 2 hidden complex roots. And yeah, if you cube either of those, you get 8. Pretty wild.
And this process works perfectly even if you start with an imaginary number. Like, what are the square roots of negative 4i? You do the exact same thing. Convert to polar, apply the root formula, and then calculate the answers for k equals 0 and k equals 1. And boom, it spits out the 2 perfectly symmetrical roots.
So you might be thinking, okay, this is cool, but is it just for solving problems in a pre-calc class? And the answer is no, not at all. This stuff has some mind-blowing applications. But before we get to the cool visuals, let's talk about a few common mistakes, because you're going to want to avoid these.
Okay, this is probably the #1 mistake people make when finding roots. Order of operations is critical here. You have to add the 2 pi k to your angle first, and then divide that entire thing by n. If you do it the other way around, if you divide the angle by n and then add the rotations, you're going to get the wrong spacing and the wrong answers, every single time. So add first, then divide.
And here are 2 other super common trip-ups. First, when you're finding roots, remember, you are taking the nth root of the radius, you're not raising it to the nth power. That's for the other formula. And second, don't forget to find all of the roots. You have to cycle k all the way from 0 up to n-1. So many people just find the first root and then stop. Don't be that person.
Okay, so where does this stuff actually show up in the real world? Well, this exact math is the engine behind some of the most breathtakingly beautiful and infinitely complex images you've ever seen. Fractals. Seriously, every time you see a picture of the Mandelbrot set, what you're really looking at is a picture of complex powers at work. Each tiny pixel's color is decided by repeatedly applying a simple formula, one that uses the very math we've been talking about.
And that kind of brings us to a final big idea to chew on. If a pretty simple rule for powers and roots can create something with infinite, stunning complexity like a fractal, it just makes you wonder, right? What other hidden patterns in physics, in engineering, in nature itself are just sitting there waiting for us to find them, all governed by the surprisingly elegant rules of complex numbers?